Okay, so this is a simple problem where we are given a sequence. We are asked to compute its endpoint DFT. To be able to do that, we need to remember three main things. The first one is we need to know our DFT formula. The second is we need to know the geometric series formula. And the third is we need to know when we are dealing with indeterminate form 0 over 0, how do we deal with that using perhaps L'Hopital's rule. So let's solve that problem. So the solution is, let's start with the Fourier DFT formula. That is n from 0 to n minus 1 xn wn kn, where remember that wn is defined as e to the minus j 2 pi over n. Okay. Now I look at this expression and I see that xn is 0 for all values above n by 2 minus 1, so I only go up to n by 2 minus 1. And then for those indices n, the number is just, xn is just 1, so I just replace that by 1. Now I want to write this in a form that you can recognize as a geometric series, so I'll just write it as wnk raised to the n. So notice this is just a geometric series like this, m from 0 to m minus 1. If I am given rm, m or n, that's just dummy variable, so this is my r, and if I do that, then my formula is 1 minus r raised to the m, the number of terms, divided by 1 minus r. Okay, so I'm going to just use this formula. So if I do that, what do I get? I get 1 minus wn k times n by 2 over 1 minus wn k. I'm going to expand that. That will be e to the minus j 2 pi over n times k times n by 2 over 1 minus e to the minus j 2 pi over n. Now here these two n's cancel, these two cancel. I get 1 minus e to the minus j pi k over 1 minus e to the minus j 2 pi over n and k. I'll simplify this further. So let's look at e to the minus j pi k. Remember that is cosine of pi k minus j sine of pi k. Now sine for any odd multiple of k is 0, and cosine is equal to 1 if k is even, and that is minus 1 if k is odd. Okay, so this means that when k is odd, 1 minus e to the minus j pi k is simply equal to 2. So my xk, so what I will do is I'll write it over here that my xk is simply equal to 2 divided by 1 minus e to the minus j 2 pi over nk for k odd. Okay, that is the first case that I have. Now what about k even? Well, when k is even, the numerator 1 minus e to the minus j pi k is equal to 0. Okay, so that is good, but we have to be careful. If the denominator is not 0, then when the numerator is 0, the answer will be 0. So this means that x of k equal to 0 for all even k such that 1 minus e to the minus j 2 pi over nk is not equal to 0. Now is there any even k? Now even k, and also k has to be between 0 and n minus 1. So is there any k for which this is not true, that my denominator is actually equal to 0? If we stare at this, we find out that yes, there is one such k, and that is k equal to 0. So k equal to 0 is the case when both numerator and denominator are 0. Okay, so when k is not equal to 0, so what we find out is when k is not equal to 0, x of k equal to 0 for even k, and k is not equal to 0, and k is between 1 up to n minus 1. Okay, so this is my second case. Now how do we solve the third case, which is k equal to 0? For that, we can either plug in directly k equal to 0 here. If I plug in directly k equal to 0, then I'll get an answer. I will have n by 2 entries non-zero, and the sum will be n by 2. So that is one approach. The other approach is you could use L'Hopital's rule. So I'll just do that. If I look at this expression, I'll apply L'Hopital's rule to this. So I'll do dxk by dk, which is equal to pi e to the minus j pi e to the minus j pi k over j 2 pi by n e to the minus j 2 pi by n k. Put k equal to 0. This means that dxk over dk for k equal to 0 will be equal to n by 2. So this means my x of k at k equal to 0, so my x of 0 is n by 2. As I said earlier, you could have obtained that by directly plugging in here k equal to 0. So when k is equal to 0, this is 1, and you are adding n by 2 ones, so your answer will be n by 2. You could have done that also. Okay, so all we have to now do, this is my third case. So this is all I have to do is now combine these three cases. So it turns out that x of k is going to be n by 2 for k equal to 0. That is due to this part. It is equal to 0 for k not equal to 0, k even, and k is between 0 and n minus 1, and then it is going to be equal to 2. So this even part is due to this double star equation, and then the last part is that this is equal to 2 divided by 1 over 1 minus e to the minus j 2 pi over n times k for k odd. So that is my solution. If you go back and look at the problem, you realize that the main steps we have done are, we started with the DFT formula, we converted it into the geometric series, use the geometric series formula, then we use Euler's formula to be careful about what the numerator is. In one case we get our numerator to be, for k odd, 2 over 1 minus e to the minus j 2 pi k over n, so that is my k odd answer. In the other case, for k even, my numerator is always 0, and in that case I have to be careful about that I don't get the 0 over 0 form. We see that the only case that happens is when k is equal to 0, so that is this case. And for that, then I could have directly plugged into the DFT formula, or I use L'Hopital's rule, I get n by 2, and my final answer then ends up being these three cases for k.